Hey, P Physics 1. This is Mr. Heinrich, and we're looking at number 17 from our summer assignment. Please pause the screen if you need to see the problem, because I'm going to transition now to my paper. Again, we're using College Physics from Serway and Vuille. Those are the authors, and it's the 10th edition. And we have this hurricane that's passing over the Grand Bahama Island in a direction 60 degrees north of west with a speed of 41 kilometers per hour. And again, they were saying that this was happening. Let's make sure it's focused there. Turn on the light. There we go. I think that'll be better. Okay, it's happening for how many hours? Well, if you look back at the pause screen from a previous moment in the video, you're going to see that it says 3 hours later, the course of the hurricane suddenly shifts due north. So that implies that we were going at this speed, 60 degrees north of west, for 3 hours, right? 3 hours. And that was speed 1. Speed 2, it says it suddenly shifts due north. So we know we're going north at a due north heading at 25 kilometers per hour. So we're moving at this new speed due north for how long? Well, if you read to the end of the problem, it says how far from Grand Bahama is the hurricane 4.5 hours after it passes over the island. Well, at the beginning of passing over the island, we're going at this speed. 3 hours later, it shifted to this speed. So wouldn't it make sense that it's traveling at this speed for 1.5 hours if our total time is 4.5 hours? Let's see. There we go. That should be a little better. Okay. So this is our raw information, and we have to take this and change it into, hey, what is my total displacement at the end of the entire trip? Which is a little bit of a trick because they didn't give us displacement 1 and displacement 2. They gave us speed 1 and speed 2. And again, if you're not really understanding this notation, look back at the previous video, number 13, that I did. But this is a change in position. R stands for resultant, also known as a total, right? You could think of it that way also. So the resultant displacement, the resultant change in position. What do you say? What is my first change in position, my delta x1? Well, if I travel for 3 hours, going 41 kilometers every 1 hour, well, doesn't it make sense we just multiply this by 3? 3 times 41, and we get 123 kilometers, right? What about my second displacement? My second displacement from my speed 2, well, if I go 25 kilometers every hour and I traveled for 1.5 or 3 halves, right? This is 3 halves. So I can multiply 25 by 1.5, or you can multiply by 3 halves. So I'm trying to do this in my head. 3 times 25 is 75 divided by 2. I think that's 37.5, right? I'm asking you like you can actually answer me. Let's just make sure that I'm not making anything up. Yep, 37.5 kilometers. Now keep in mind, this is 123 kilometers at that bearing, right? This is 37.5 kilometers at that bearing, due north. Let's talk about interpreting something like this, 60 degrees north of west, because what I need to do is find this, but until I know how to do that, can't really move forward, can we? So I'm going to draw a little compass rose here. This would be north, this would be south, this would be east, and this would be west, right? So here's how we interpret this. I always tell students, read it backwards, right? Who do we belong to? Who are we of? We are of the west in this bearing, right? We are of the west. Boom. I'm pointing my pen west. Which way do I swing? I swing to the north. How many degrees? 60 degrees. So I literally read it backwards. I am of west, and I swing to the north, meaning I rotate to the north 60 degrees. So it looks like I'm 123 kilometers. $60 north of west. Right? 60 degrees north of west. See if that works better. Yes, finally we have good quality light. There we go. Okay, so I hope that makes sense. Let's do another one for practice real quick because I know it's new for some of you. Let's do another north-south. This one will obviously not be the question. It'll just be one I make up real quick on the side here. Woo, this is a made-up one. So I'm going to say, let's say I'm going, I don't know, 100 kilometers east of south. We could do that, right? East of south. Who do you belong to? You belong to the south. And you're going to swing. Oh, I didn't even give us a degree, did I? My fault. 40 degrees east of south, right? So we belong to the south of the south. We're going to swing or rotate 40 degrees towards the who? Towards the east. Of south, go east 40 degrees. About there, right? About there. And if that's 123, 100 better be shorter, right? Our magnitude better be a little smaller, so maybe that. Notice that corresponds with what I just said. The 40 degrees goes there. And this is 100 kilometers. How else could we state this? You might already be thinking it. 100 kilometers, 60 degrees south of east. Wouldn't that be the same exact vector? Because we would start on where? We'd start on the east and we'd swing to the south. How far? 60 degrees. So you can see this is two different ways to state the same thing. But this is not even the problem, is it? So I hope that makes sense. Back to this new piece of paper. We need to draw a vector diagram that represents those two displacements. Let's do that now. Here we go. So I'm going to draw that first one, 123. Oop, that's not really 60 degrees, is it? Maybe like that? Yeah, there we go. That looks like 60 degrees. From what? From what? Well, if you need a little reference axis, that's a good thing to draw. So I'll just draw a little dotted reference axis, right? And that's 123 kilometers. Remember, this is, what was it? North of west, right? And then if you look back at the previous video, you'll notice that when I'm adding two vectors, I need to put the next vector's tail on the head of the previous vector I just drew. And we call this head to tail vector addition. So I'll use a different color for this one. And I need to draw this one like, maybe that's 37.5 kilometers, right? You want them to be relative in their lengths to each other, right? 37.5, 123. And that is the beginning of hopefully the end of this problem. Now here's the problem. We can't just add these, right? We could add them if they were acting in the same axis, right? If they were both acting in the y-axis or both acting in the x-axis, we could add them or subtract them depending on their directionality, right? If they're acting opposite directions, we subtract. Same direction, we add vectors. But since they're not acting in the same axis, we can't do that. What is the workaround that we use? We must take our angled vector and break it into components. So I need to break this angled vector, which is acting both in the north and the west. I need to break it into a west piece, and I'm just going straight for it. The west piece and the north piece. And notice I didn't take a lot of time to think about it. I know that this maroon vector must be broken into a west part and a north part. You might be asking yourself, well, couldn't I go north and then west? Absolutely. If you did that instead, you would still have the same length north and the same length west. So if you're looking for a method that always works, you start at the tail of your vector that you want to break into components, and you go from the tail to the head, either moving left, right, up, or down, right? So what did I decide to do? I decided to move left and then up, right? To get to the head of the maroon vector, right? So this maroon vector has now been replaced with its two component parts. In fact, once I find the amounts that go here and here, I don't even need this maroon vector. I could be really dramatic and just scribble it out because it's that unimportant once I have components that explain this vector. Now that is going to take some trig, right? And here's the part you're not going to like also. I called this delta x1. Well, what does that make this side here? The notation gets a little cumbersome, right? This is displacement 1, the x piece. The x component of displacement 1, right? This is displacement 1, the y piece. And maybe I should be using maroon here so I'm not confusing you. This vector right here, this vector is a portion of this guy right here. This vector is the north piece of this maroon vector, right? So the y piece, the x piece. All right, enough of that. Let's get into the math. Well, if I'm looking for an adjacent, this is a triangle, right? A right triangle. If I'm looking for the adjacent side and I've got the angle and the hypotenuse, well, that sounds like cosine to me, doesn't it? The cosine of 60 should be the adjacent side I want, delta x1x, over the hypotenuse, 123. And while I'm at it, before I get my calculator out, what about this guy right here? Isn't this side right here of the triangle? This side is the opposite. It's opposite from the angle. So I would use sine of 60 equals the opposite side that I want, which I have labeled this, right? I've labeled it delta x1y. That's the opposite side over the hypotenuse. Now you'll see here that if I want to solve for these sides that I don't know, I would just clear my fraction by multiplying both sides by 123. I will conveniently use that dash as a 1. There we go. And then this would also get the same treatment, right? 123, 123, and boom, boom. There we go. And so cross that out, cross it out. I just have to do 123 times the cosine of 60 and 123 times the sine of 60. Let's do that real quick. 123 cosine 60. This sucker right here turned out to be 61.5, and we can see that it's west. I don't even need to write west because the arrow, shows that to us. And then the other one, 123 sine 60, is this guy right here ends up being 106.5. 106.5. And these are both kilometers. I do like it when you write units. It makes me feel like you understand you're not in a math class, you're in a physics class. Okay. Now, why did we do all that? Because earlier I said we can dramatically just cross it out. I don't even care about that vector because I replaced it with its west piece and its north piece. And can you see right here? I got a teal vector and a teal vector. They're both going north. Man, I should probably add those, right? So I'm going to add them together. And now I'm going to start working on summing up all of my y's and summing up all of my x's. So that's always how we do vector addition. We take the raw vectors, we put them head to tail, which I did here before I scribbled it out. Then if any of those vectors are angled, we go ahead and we resolve those into components, which I did here through all this work. And then once everything is in the y-axis and the x-axis, we can add our vectors together very simply. So up here I'm going to write sigma, the sum of my displacements in the y-axis would be this 106.5 plus this 37.5. Again, I'm adding them because they're heading the same direction. And I know this comes out to 144, is that right? I'm pretty sure it is. I'm going to go for it. I'm just going to think that's right. I better do it. Plus 37.5. Okay, yeah, I was right. Okay. All right, then I'm going to sum up. Now, this seems like a nonsense step, and I understand that, but I'm trying to show you the process here. What are all of my vectors added together in the x-axis? Well, there's only one in the x-axis. How much is it? 61.5 kilometers. Which way? West. By the way, which way was this one? North. And hello, what did I just come up with? I just came up with the y component and the x component of my final triangle. Final triangle of who? Of delta xr, the very thing I've been looking for this entire problem, right? So what do I mean by that? Let me show you. I'll draw it right here because it'll be a nice parallel. So ultimately, what did this storm do? It went 61.5 kilometers west, and ultimately from there it went 144 north, right? That's what it did. I could have kept with my original drawing, but I usually like drawing a whole separate drawing for my final answer. And if you look back at the previous video, my result goes from the tail of my first vector to the head of the last vector. That is to say, it goes from where I started to where I stopped. My change in position is from here to here, and I call that my resultant displacement. Can you just trust me that that's Pythagorean theorem? We need to kind of hustle here. I'm running out of space on my phone. That would be this squared equals that squared plus that squared, right? So 61.5 squared plus 144 squared. There we go. I'm going to do that math. 61.5 squared. I'm doing the square root at the same time, by the way. Plus 144 squared. And I end up with this 156.58. You're going to find out I said this in the last video too, I'm not a big stickler on rounding. In fact, just to keep numbers easy, I'm going to really go up and just make it 157. If you put 156.6, that would have been fine, but I'm going to go 157. Now remember, this is not a complete answer. I need a bearing. I need a direction. A magnitude and a direction is a vector answer. You need a magnitude and a direction to explain a vector. How about this? I'm going to set up an XY axis here. Where do I set it up? At the tail of my resultant vector. Always set up your XY axis there. Now look at this. This angle makes a lot of sense to find because it's included in our triangle, right? Over here, I'm going to write, again, look back at the last video, I'm going to go straight to the inverse tangent function. The inverse tangent of opposite over adjacent will get me that angle, and we end up with an angle of 66.87 degrees, yeah, 66.9. You can see where I just want to call this thing 67 degrees. Yeah, it's roughly 67 degrees. Now, you might think, hey, that's it, we got it, 67 degrees. But we don't. I'll tell you what, if you had found this angle, like if it was this one right here, like let's say the vector was actually over here, it's not. Let's say it was over here, 67 degrees would be fine. Because whenever you state an angle and you just go from the positive x-axis, we just state it as a degree. However, look at this, we're in the second quadrant. Wouldn't it be 67 degrees? Who do we belong to? We are of west, aren't we? Because look, the angle is touching west. I'm going to write in here of west. I hope you can see that. That's an of, I'll write it here, of west. And which way did we swing? We swung to the north of the west, right? Of west, we swung north. So we are 67 degrees north of west. And that is a correct answer. Also, it would be correct to find this one right here, right? But let's not worry about that. We're good. Have a great day. Bye.